All right, so let's take a look at this elastic collision example. So we have a particle, two balls that are moving with, one's moving with the speed v0, the other one is at rest. They're going to collide elastically. We're going to assume that we are on a frictionless surface, so we have no net external force. So I'm going to define that my change in momentum is equal to 0 since my net external force, since my net external force is equal to 0. I'm going to define that change in momentum is 0. I'm also going to define that my change in kinetic energy is going to equal 0 because elastic. So you need to make sure that you start off with your definitions of your conservation laws, because that is what provides the foundation for the math that you're about to do. They will look for that. There's usually points for that on FRQs. So then, because I'm looking for the speed of each of the balls, that means I don't know what either of the speeds are. It's elastic, so they can't be stuck together moving at the same speed. So therefore I have two unknowns, so I'm going to need both of those equations. So let's start off with the momentum equation. So I'm just going to call object A and object B just because it's easier at the start. So I'm going to do MA VA1 plus MB VB1 is equal to MA VA2 plus MB VB2. And then I'm going to define VB1 at the start to be 0 because that one starts off at rest. I didn't write that in the problem, but this just starts off at rest. Sorry, let's try to shorten the overall wording. And then I'm going to sub in the variables that are provided in the problem. So MA is just M, VA1 is V0, and then MA is still M, VA2 is unknown, and MB is 2M, and then VB2 is also unknown. So one thing that is nice is that the mass M does cancel out. You can work this problem even if the mass doesn't cancel out. It just gets really long. I did have a solution for how to do this without the masses being equivalent multiples of each other. So it just takes a lot more paper, and I don't have much paper here, which is why I shortened this by making the second mass just a multiple. Because you'll get the same process going either way. And then in terms of the kinetic energy, we're going to have 1/2 MAVA1 squared plus 1/2 MB VB1 squared plus 1/2, oh no, not plus, equals 1/2 MAVA2 squared plus 1/2 MB VB2 squared. And then once again, VB1 is 0, so that term goes away. The halves cancel, which is nice, simplifies things down. MA is M, VA1 is V0, and that's going to equal M VA2 squared plus 2M VB2 squared. And my mass cancel out again. Be really careful when you're subbing in. I honestly worked this problem about 6 times, knowing exactly what I was supposed to be doing. I couldn't find my mistake, and that's because I kept erasing it back to a part where my mistake was still present. So this 2M right here, I had forgotten the 2, and I was getting things that didn't make sense. So be very, very careful when you're substituting in your values. So we get V0 squared is equal to VA2 squared plus 2 VB2 squared. So now I have 2 equations and 2 unknowns. So what I'm going to do over here is I'm going to solve this for VA2. So VA2 is going to be V0 minus 2 VB2. And then I'm going to plug in over here. So I get V0 squared is equal to V0 minus 2 VB2 all squared plus 2 VB2 squared. And then I'm going to need to expand that term. So I get V0 squared is going to be V0 squared minus 4 V0 VB2 plus 4 VB2 squared. So that's just distributing that all out to all the terms, plus 2 VB2 squared. And then what I can do is I can group like terms. So I'm going to get 0 is equal to, oh, well, when I subtract that v0 squared over, those are going to cancel out. So I'm going to get this negative 4v0 vb2 term. And then those add up, so I get 6 vb2 squared, not 5 like I was getting earlier. If I wanted, I could divide all of this out by 2. So it's going to be 2, and that's going to be 3. And then I end up being able to factor out vb2. So I get 0 is equal to vb2 times 2v0 plus 3vb2. And then I could set both of those sides equal to 0. So this vb2 here being still at rest doesn't make sense. So that is not going to be our solution. So if I solve over here, I'm going to get vb2 is equal to 2/3 of v0. And that actually kind of makes sense. Because it's twice the mass, it's gonna retain essentially. It's gonna gain quite a bit of the momentum, whereas the a over here term is gonna lose a little bit less. So kind of fun on that one. Once we have vb2, we can come in and sub in over here and find va2. So va2 is going to be v0 minus 2 times 2/3 v0. So va2 is going to be v0 minus 4/3 v0. So va2, so that would be 3 over 3, is going to equal negative 1 over 3 v0. So basically what that tells us is it tells us that va2 is moving backwards, whereas vb2 is moving forwards. So that gives you a way to solve the problem. So you actually had to use both kinetic and momentum equations in order to solve this problem. You can always go back and plug these into individually into the left and right side of the momentum equations to make sure that it did calculate out correctly.